Hello guys, welcome to another concept on Introduction to Ordinary Differential Equation. In this lesson, we shall consider equations whose variable cannot be separated but can be reduced to separable variables by a change of variable. This group of differential equations is called homogeneous differential equation. To begin with, let's dive into the definition of homogeneous function. A function f at xy is called homogeneous of degree n if it satisfies this fundamental property. That is, where the lambda is a scaling factor. In other words, where this lambda is what we use to multiply through by the function f at xy, and n is the degree of homogeneity. What this means is that for us to verify whether a particular function given, say f at xy equals x squared plus y squared, is indeed homogeneous function, then we need to scale this function with a scalar called lambda, and after that is done and we're able to factorize the lambda out onto a particular degree n, then that particular function can be said to be a homogeneous function. For clarity, let's consider these examples. So this problem says determine if the following functions are homogeneous or not. So this is our first example. Let's look at how you can check whether it is homogeneous. We're given f at xy equals x squared plus y squared. First of all, we said that we should scale the x with lambda and then the y with also lambda. This simply implies that this takes the place of x and this also takes the place of y. So if that happens, it means we're going to have lambda x squared plus lambda y squared, which we are going to get lambda squared x squared plus lambda squared y squared. Consider lambda squared is common, that will be factorized out and we are going to get x squared plus y squared. We're given that y f at xy equals x squared plus y squared. So we can replace that with this and that will give us this, which simply means we have a lambda of degree what? 2. Since we have been able to factor the lambda squared from this particular function without having any lambda in it, hence it is a homogeneous function. So therefore, this is how we show that a particular function is homogeneous or not homogeneous. Sometimes you can easily look at the function and tell that it's homogeneous or not. Or this is clear. You can easily find the lambda squared and here to be a lambda squared. So when you factor lambda squared out, you get the same thing back and hence it's homogeneous. With our second problem, we're given f at xy equals xy plus y squared. And here too we can tell easily that it's a homogeneous function. Why? Because when this is scaled, we are going to get lambda here to give us lambda. Lambda times lambda will give us lambda squared, and this will give us lambda squared. So here we get lambda squared over here. When the lambda squared is factorized out, that will be homogeneous function. But let's prove it. So we know that f at lambda x lambda y is equal to, so this we're going to lambda x dot lambda y plus lambda y all squared, and that will give us lambda squared xy plus lambda squared y squared. So we can factor the lambda out. We're going to get lambda squared, then this will give us xy plus y squared. And with that, we can say that f at lambda x lambda y is equal to lambda squared f at xy. So since this is out without having any lambda in there, we can say therefore Also, let's consider this. So now scaling, we are going to get equals sine of lambda x dot lambda y on cosine of lambda x dot lambda y, and that will give us sine of lambda squared xy on cosine of lambda squared xy. You cannot factorize the lambda squared out. Why? Because since it is an argument, we cannot factorize a x squared out. This can also be factorized out. Somebody will say that, okay, then let's cancel. We cannot cancel either. So we can say that, therefore, our fourth problem. So we are going to have f at x, y equals, and our f at lambda x, y equals cubic root of lambda cube s cube plus lambda cube y cube. And with that, we are going to get cubic root of lambda cube by s cube plus y cube, which will give us cubic root of lambda cube, then cubic root of s cube plus y cube, and this will give us lambda to the degree of 1 dot cubic root of s cube plus y cube. So this is the same as this function, and so we can say that this is what homogeneous with degree 1. Our fifth example. So let's scale it. Lambda x lambda y equals lambda cube s cube plus lambda x lambda squared y squared e power lambda x lambda y. And this will, when we simplify, I get lambda cube s cube plus, so the whole of this will give us lambda cube x y squared. And remember, this can go to, this can cancel that, so we're going to get y. And now we can factorize this out, so we're going to get lambda cube by the whole of what we have there, x cube plus x y squared e power x y. And you can see this is the same as what we have here, and since there's no lambda in there, we can say therefore let's look at the main concept, that is homogeneous differential equation. When do we say that a particular differential equation is homogeneous? A differential equation is said to be homogeneous if its corresponding function is homogeneous function of degree 0. So here, what we are trying to imply is that for a particular differential equation to be said to be homogeneous, the function of that particular differential equation must be homogeneous, but not alone. The degree of that homogeneous function must be 0. So let's look at these examples and see whether they are homogeneous function or not. Obviously, this is homogeneous differential equation in the sense that when we put the lambda here, we are going to get lambda squared. So when we factorize that out, we are going to get lambda squared. This also produces lambda squared. A lambda squared in a division, we know that we are going to subtract, and that will give us lambda power 0, and hence the homogeneous differential equation. But let's prove. So we say let our derivative equals a function at xy. So if that is the case, then it means our function now becomes f at xy equals x squared plus y squared on xy. Let's scale it, and that will give us lambda x lambda y and that gives us lambda squared x squared plus lambda squared y squared on lambda x lambda y, which we know clearly that this we are going to get lambda squared x squared plus y squared on this will also give a lambda squared xy. So you know from indices this can be written as lambda power 2 minus 2 by x squared plus y squared on xy, which we are going to get f at lambda x lambda y to be lambda power 0 x squared plus y squared all on xy. So since the degree is now 0, from the definition we can say that therefore let's look at the second example. We are given dy dx equals root of x squared plus y squared on x. So we say let our dy dx equals f at xy equals x squared plus y squared on x. F at lambda x lambda y equals root lambda squared x squared plus lambda squared y squared on lambda x, and that will give us lambda squared x squared plus y squared on lambda x, which will give us lambda squared x squared plus y squared all on lambda x. Lambda root x squared plus y squared on lambda x, which this will give us lambda power 0 root x squared plus y squared on x. That. So we can say that since we have been able to factorize the lambda out and the degree is 0, hence it is also homogeneous differential equation. So therefore homogeneous differential equation. So we can see obviously that it's homogeneous differential equation in the sense that this will give us lambda squared, this also produce lambda squared, this also produce lambda squared, all divided by lambda squared. So when lambda squared over here is factorized out on the lambda squared, it will give us degree what? 0, and it is what? Homogeneous differential equation. So we say let our dy dt equals f at ty. So our f at ty equals lambda squared y squared minus 4 lambda y lambda t plus 6 lambda squared t squared all on lambda squared t squared. So you know this will give us lambda squared. So when we factor lambda squared out, we are getting y squared minus 4yt plus 6t squared all on lambda squared t squared, which you know you are going to get lambda power 0 bracket y squared minus 4yt plus 6t squared all on t squared. So we can see clearly that we have it. This is homogeneous in the sense that we're able to factorize all the lambda out, and then degree here is what? 0. Our final problem. So the question is this indeed a homogeneous differential equation? It is clear that it's not. Why? Let's see. So let's f at ty equals dy dt. Our f at lambda t lambda y equals lambda t sine lambda t lambda y. Our lambda t sine, this will go to 1 and we are going to get t on y. But here
the power is 1. Since the power is 1, though we're able to factorize that the power here is 1. Therefore, our dy dt equals t sine t on y is not homogeneous differential equation.
That is that for the homogeneous differential equation. Our next concept, we're going to look at solution to homogeneous differential equation. Thank you very much for watching. Subscribe, like and comment, and share to your colleagues. Bye bye.